Lecture 19 covers sections 6.3 through 6.3.1. At the end of today's lecture, you should be able to solve statically indeterminate systems using the compatibility equation method. Now, a statically determinate loading problem is one where our internal reactionary forces, or our applied reactionary forces, of a structure can be resolved using solely our equilibrium equations. A statically indeterminate loading problem is one where the number of unknown internal reactionary forces, or applied reactionary forces, exceeds the number of independent equilibrium equations. To rectify such systems, i.e. statically indeterminate systems, we will use equations of deformation. Now, consider the following system below. Is it statically determinate? In our system, we have an aluminum rod inserted within a steel tube. There's a rigid plate at B for which we apply a load of 1,000 kilonewtons. And we recognize that this problem is not statically determinate, i.e. it is statically indeterminate. For our aluminum and steel tubes are both going to exert reactionary forces, R1 and R2, to resist our applied load of 1,000 kilonewtons. Thus, our equilibrium equation would be R1 plus R2 would be equal to minus 1,000 kilonewtons. We have one equilibrium equation, i.e. the summation of forces in our x direction, and two unknowns, R1 and R2. To solve statically indeterminate problems using the compatibility equation method, we will use the following solution algorithm. First, we will draw the free body diagram of the system of interest and apply all pertinent equilibrium equations, summation of forces, and summation of moments when applicable. If the number of unknowns within our system exceeds the number of equilibrium equations, we will draw a displacement diagram and construct the compatibility equation that characterizes the deformation of our system. Within our deformation equations, we will substitute the forces from the equilibrium equations into our deformation equations. Thus, we provide a relation between the two sets of equations. Now, we will repeat this until the number of equilibrium equations and deformation equations equals the number of unknowns.